All right, good morning. So welcome back. I hope most of you made it back. So yesterday we started talking about laminar premix flames, and we started talking about flame kinematics. Just to look again at what we want to do, we want to look at kinematics and the burning velocity as a very important parameter, and then in the next lecture we want to talk about details of the flame structure. Here we want to talk about the kinematic mass balance, burning velocity, how to measure burning velocity, how to compute burning velocity. Then we'll introduce an equation that you can use to look at flame dynamics, and then finally we'll talk about modifications to the burning velocity which could lead to instabilities. So this we talked about last time. We said premix combustion is good for getting heat release in a very small volume. We said, but it can be dangerous at the same time. You can get flashback, instabilities, and things like this. We talked about how the flame looks like. You see there is a thin reaction zone here, and that's where all the action takes place. This is where we ended last time, so I'll review this again. So you have in the premix flame, you have like here, let's say you have a fuel air mixture here in the center, and then you have a flame burning into this fuel air mixture, and then you have hot combustion products behind the flame. And so this, I mean, in a one-dimensional setting, this is how this would look like. You have the fuel and the air. They are convected towards the flame. They don't burn because they're cold. And so while they approach the actual flame front, they approach this region of high temperature. And because the temperature in the unburned is low, and in the burned it's high, you have diffusive thermal energy flux or heat conduction from the burned into the unburned, which basically heats up the unreacted gases. At the same time, because the fuel and air, they are consumed in the burned, or let's say for a lean flame the fuel would be consumed, maybe there's some oxygen left over, but it's much smaller than what you have in the unburned. There's also a gradient of the reactants, and you have the reactants diffusing into the front. So they approach this convectively, but then they diffuse into the front. And now this is a zoom into the really, the core region of this flame. Really, these gradients are very, very large. And so these diffusive fluxes, the heat flux, heat transfer, and also the flux of fuel and oxidizer, they're very, very fast. And okay, so then you heat up here the gases up to a point where they can ignite, where the temperature is high enough that you have chemical reactions. This is what's called here the ignition temperature. We'll see later on that when we talk about one-step chemical kinetics, you can imagine one-step chemical kinetics. At what temperature does the reaction rate go to zero? The point is it never really goes to zero. It just gets exponentially small. So if you have a one-step chemical reaction, you go to lower temperature, the reaction rate gets exponentially small, but never really reaches zero. But so you have to somehow artificially define this Ti. For multi-step chemical kinetics, we'll see later on, there's a very, very distinct temperature where things happen, where things start happening, or you get extinction if you're lower than that temperature. So we'll talk about this later on when we talk about flame structure. Okay, so that's what's happening. The gases here are heated up to that temperature, and then once they're at this temperature, then things take off and chemistry happens, and then you get a heat or temperature increase here by chemical reactions. And then whatever is left over, here fuel is usually entirely consumed. Whatever's left over here from the oxygen, that is then just convected downstream. I mentioned last time, for lean flames, you have oxygen left over. For rich flames, you don't have oxygen left over. In the limit of a one-step global reaction, you would have fuel left over. But in real life, the fuel is always converted to CO, and then the CO and hydrogen would be left over here. Okay, so let's talk about the kinematics. Let's just look at a simple experiment, a Bunsen flame. We looked at this here, although this is not exactly a Bunsen flame because you have, you have a bluff body inside this nozzle I showed you, and so we have a bluff body inside here, and so that generates turbulence. And so you saw last time we have a turbulent flame really coming out. But you have seen a Bunsen burner. You have fuel coming in here. You suck in air here, maybe through these holes, and then this is pre-mixed, and it comes out here. And if the velocity is low enough, then it's laminar, and you get this Bunsen cone here. You can then close here with this little wheel here. You can close the airstream. And closing the airstream then would give you, this just closes it up or down. But typically in a Bunsen burner, you can also close these air holes, and then you just get a diffusion flame like what I showed you here. So this is how this looks like then, and then we can look at the kinematics here that happen. You have a velocity. So look at this right side here of this Bunsen flame, and this flame is shown here as this oblique flame front. And then what you have, because it's steady state, you have a velocity that goes into the flame, and then you have the burning velocity, and they just compensate. Okay? But you see the flow here is, of course, is not normal to the flame. And so what we can do is we can just take this velocity. So this is the incoming velocity here. And we can split this up into a tangential component and a normal component. And then you see the normal component goes into the flame, and that is the same as the burning velocity. That's what the burning velocity has to overcome. And then you have, through the flame, of course, you have a density change, and the flow will be accelerated. And so the velocity in the burned gets a little larger than in the unburned, and you have a tangential velocity here. The tangential velocity does not change, and then what you see is that the flow coming in here, is these two velocity vectors, and coming out you get an acceleration of the normal component, but not of the tangential component, and that's why the streamlines are deflected through the flame. Now, if you you see that you can actually, determine this normal velocity here if you know the angle here. The angle is the same as the cone angle. And so you could imagine that you take a Bunsen flame and you just measure this angle, and you know what the flow velocity is, and then that is an easy measurement for the burning velocity. Okay? That's one thing you could do, but it's not so accurate, because what you see here is maybe it's not exactly a straight line here like this. There are things happening here. You have heat losses here to the burner, which change the burning velocity, which change the local enthalpy here. And then also, what else? It's not so accurate to measure this angle and all of this. So this, in principle, you could think that's a good way. Oh, the other thing I want to say, maybe it's also hard to get a exactly top hat velocity profile like this. Usually in a laminar, in a nozzle here, you have a laminar profile, which is a parabolic profile. You could try to straighten out the flow and all that, but it's not a very accurate measurement. But if you want to do this at home, that's one thing you could do. So then you see immediately that if I increase the velocity here, then this angle here, it becomes shallower, but the burning velocity will be the same. Or because the burning velocity will be the same, you have to increase here the tangential component, basically, which makes this shallower. So then if you have measured this angle, then the burning velocity here is just, the same as this velocity, which is the incoming velocity times the sine of this angle. Okay, it's very simple. What's interesting here is how do we define this value here that we call burning velocity? So burning velocity is, you could say, that is the speed of this flame relative to the gases, surrounding this flame. Now you have a different velocity ahead of the flame and behind the flame, so you need to say what relative velocity you mean. Okay? So typically, you could either say this is the burning velocity with respect to the burned, or you could say this is the burning velocity with respect to the unburned gases. Okay? Typically, we say we're interested more in the burning velocity with respect to the unburned gases because this gives you the mass burning rate also of the fuel. Okay, very easily gives you this mass burning rate. So, when we say SLU, we mean this is the velocity of this flame with respect to the unburned gases. Okay, and then SLU is the same as this. SLB would be the same as VNB. So you see that would be larger in this case. Okay. What else? You see that at the flame front is you could look at it like a discontinuity. It's very thin. So for the purpose here of the kinematics, we want to say it's infinitely thin, and then mass has to be conserved through the flame. So the mass flux into the flame is rho times V times A times some area in the unburned, and that has to be equal to the mass that comes out on the other side. Rho times Vn times the same area, so the area is taken out here. But then you see the ratio of the normal velocity in the burned compared to the normal velocity in the unburned is the same as the density ratio. Okay, so density increases, the density decreases through the flame, and so because of this, the velocity increases. And here you see again what I said earlier is that the streamlines are deflected here by the expansion through the flame. Okay? Okay, so one thing that's interesting, I said the flame burns normal to itself, and also it burns into the unburned gases with this burning velocity. But you see that this doesn't hold really at the flame tip, because at the flame tip the flame has to be horizontal somehow and needs to burn right into the incoming stream. So the burning velocity at that point needs to be exactly the velocity, or the incoming velocity, which we said earlier is larger than the measured laminar burning velocity. And so turns out at the tip, other effects are important. The curvature effect here is important. It turns out that the curvature here becomes of the same order as the flame thickness, and then the curvature can affect, how the flame burns. Okay, that's important. We said earlier the flame is thin, and if the curvature radius is much, much larger than the flame thickness, then the flame thickness doesn't know. The flame doesn't know about curvature. Okay, they have to be of comparable order, and then they can influence each other. Good, so here explanation, the strong curvature here, the curvature radius now is of the order, it has to. I mean, this thing will become pointier and pointier until you have a curvature that is of the order of the flame thickness, and then, Lewis number effects here, they lead to the curvature effects and so on. And we'll talk about more about this a little later. Okay, burning velocity, I said you could potentially measure the burning velocity like this, but there are other ways how to measure the burning velocity more accurately, and one is this spherical constant volume combustion vessel. This is how this works. You have a spherical chamber, you have electrodes that lead to the center here of this chamber. So then you put a spark there. It ignites. So this is filled with a mixture of fuel and air. Let's say exactly the mixture of fuel and air that you want to know that you want to know the burning velocity for. So the pressure you're interested in, the temperature, equivalence ratio, everything, dilution, whatever you want. So you spark it here in the center. You initiate a flame, and the flame then moves spherically outwards. And then here you have observation windows, and then you look at the how this flame moves. And so what's measured here is what I call here the displacement velocity or the displacement speed, and that is just the displacement of this flame. I mean, it's the observed movement of the flame. And so if you want to compute or determine the burning velocity, then this kinematic relation here is important. Basically what this says is that this displacement velocity you see, that is composed of just the background velocity. Let's say you had the burning velocity was 0, but you have a background velocity, then that background velocity would still carry the flame, and you would see a movement of the flame even though it doesn't burn. Okay, so that's this first part here. And then the second part, of course, in addition to just the background velocity that moves the flame around, it also burns, and so you see the propagation. Okay, so the observed displacement speed is the background velocity that just carries the flame around plus the burning velocity. In this simple setting here is it's spherically symmetric, so it's a one-dimensional system. It's enough to write it like this. Of course, if you have a three-dimensional velocity field, the velocity might go this way and the burning velocity might go the other way. And we'll talk about this later. So both the flame front position and the displacement speed, they are unsteady. They change with time. The pressure now in this vessel, because constant pressure vessel, the pressure will increase, and that will contaminate your measurement. But if you measure, if you observe the flame only in the very beginning, when the burnt volume is still small compared to the whole volume of the chamber, then the pressure increase is very small and it can be neglected. So that's what people do. That's why the observation window here is also so small, because you're really only interested in the initial change. So there is an influence here also of the curvature, and we'll see later on that the burning velocity, or the speed at which this thing moves, or this observed burning velocity here, it changes due to the curvature of the flame. Okay, so this is an example for this. There are many of these chambers, combustion chambers around the world. We have one in Aachen. This is our setup. There's one here at Princeton also, which you might have seen during the lab tour. So you see this thing is heated here, goes to high pressure. These are the electrodes. This is the observation window is here. And then, so this is what you see. This is kind of a Schlieren technique. And then you see it's initiated here. And then you get a really spherical propagation here. So now, and this is the optical setup.
Is there heat transfer going on between the electrode and the flame boundary on the lower side of the electrode? It becomes kind of non-spherical with large radii.
Yeah, I think it's the heat transfer, but it's also just the no slip condition that you have. You will see you induce a velocity, and that is just decelerated there at the electrodes. The electrodes here, they come in like this. They come in like this, so they don't come from opposed sides. They come in from the side, so that you have a disturbance just here in this corner, and all the rest is not disturbed. And then you do kind of a fitting of the overall shape. Okay, so I just modified the slide here a little bit this morning, so the version you have is a little different, but thought this is easier to understand here. So the velocity relative to the flame front, the velocity relative to the flame front is the burning velocity. Okay, if I sit on the flame, I move with the flame, then the velocity just ahead of me, that's the same as the burning velocity. Okay. So, so that's how I burn through the unburned gases. So so this is different. This velocity is different in the burned and the unburned region. And using this kinematic relation, we can write it both in the burned and the unburned region. You see then the velocity with respect to the unburned is the RDT minus VU, or the opposite of this, which is shown here also. And then in the burned side is VB, the velocity in the burned minus the RDT. And so these are the velocities that they just come into the flame and that just go out of the flame. And so if you, again, do the mass balance across the flame, then you have the density in the unburned times the velocity in the unburned is then equal to the density in the burned times the velocity in the burned. And then what's interesting here in this particular setup is that you see you spark it in the center, and because it's symmetric, the flame moves out. And now it's not the burnt gas that accelerates, because you see on this side, the burnt gas wants to accelerate to the left. And on this side, it wants to accelerate to the right. And because it's symmetric, the velocity in the burnt is zero. Instead, the flame pushes the gas ahead of itself. Okay? So you get an outward flow. It's like an explosion where you really induce a flow away from the flame. Okay? And so VB is zero, and VU here is non-zero, because that's pushed away from the flame. And then so you have this relation here between the unburned and the burnt gases. Okay, if I now use this kinematic relation again, I plug it in here, then I get something like this. The RDT is equal to VU plus SL. And then I can solve this here for VU, and using this flow velocity on the unburned side. And I can compute here the flow velocity on the unburned side as function of SL. Okay, so this is the flow that's in the unburned mixture that's induced by the gas expansion. That's given like this. Now I can plug this back in the kinematic relation, and I get SL. In the unburned is rho B over rho U times this displacement speed. Okay, that's basically the final result. So what you measure is the RDT, and what you get out of it is this SL value. Now, what I said earlier is that this measured SL value, it still depends on the curvature, so one has to correct for these curvature effects, and I'll show you in a minute how to do this. So again, there's a burning velocity with respect to the burned and with respect to the unburned, and they're just related here by the density ratio. Yes. Yeah, that's the. So typically you assume it's equilibrium, but there are uncertainties related to this. For it turns out when you have non-unity Lewis numbers or strongly non-unity Lewis numbers, the temperature in the burn is not really constant. I mean, it does funny things, and then the other thing is you have radiative heat losses maybe, and the radiative heat losses also lead to a decrease in temperature, increase in the density. So that's one of the major uncertainties of this. There's currently, I mean, just in case you're interested, there's currently a group of people all around the world who run these chambers, who try to determine what the uncertainties are. You're comparing different techniques with each other. There's another technique where you don't need to know this density ratio. So again, here you just assume it's equilibrium. But you could also start out with, just with, let's see, this kinematic relation. If you seed particles in this thing, and then you measure the velocity here just ahead of the flame, doing PIV. Okay? Then you know this velocity, you measure this the RDT, and then you get this burning velocity. So we're currently doing, using these different techniques to compare what the uncertainties are. Okay, so here, anytime we say SL, we mean SL with respect to the unburned. That's all I want to say here. because that's usually the more important quantity. Okay, so that's how you would measure the burning velocity. It's interesting also to try to understand how the flame structure looks like. Flame structure means how do the species vary across the flame. You know, for example, you have no radicals ahead of the flame, you very small radical concentrations behind the flame, and so radicals, you peak in the flame, and knowing all these things is interesting. There's one experiment that's often used for this, and this is just a flat flame burner like this. There's a company, McKenna, I think the company is called McKenna burner. So the thing is called McKenna burner. That's kind of a standard burner that people use. I think it's a little different from here. It's not a McKenna burner. But basically what this is you have a burner, or you have a tube, let's say, and then you have maybe a porous material so that the flow that's coming out is exactly has the same velocity everywhere. And then, so this premixed gas, and then you get a flat flame like this here, okay? And so now you see here, especially in the center, there are no changes in radial direction. So if you look at the governing equations, you can drop out all the terms in let's say this is x. You can drop out all the terms in y and z, all the derivatives in y and z, and you have one-dimensional equations. So it's very simple. So in chemistry, flame chemistry, it's always important to identify a configuration where you can do measurements, but also where you can do simulations easily with detailed chemistry. Okay? Detailed chemistry simulation of a complex fuel, 1D, that's possible. 2D is very hard. It's very hard already. 3-dimensional is, with detailed chemistry, complex fuel is impossible. Okay, so that's what this is. So it's the flat flame Bunsen burner, the flat flame burner. Interesting is what happens if the flow velocity is larger than the laminar burning velocity. Say it again? It will just blow off. Okay? So this means does this mean you need to, what happens if the flow velocity is smaller than the burning velocity? Flashback, but this thing is stable, it doesn't flash back. Do you think this is done so that the velocity is exactly equal to the burning velocity? That wouldn't be stable, I think, because it would, do funny stuff. Why doesn't this flash back?
Because it can't propagate through the solid material. The channels are too tiny.
Yeah, I mean, that's one reason. It can't go in the solid material because the channels are too small. There's a minimum channel width or whatever such that the flame can propagate into it. But once the flame approaches this solid body, or not solid body, this porous material, also there are heat losses because the temperature at some points will start having a gradient. You have heat losses. What happens if you have heat losses? The burning velocity gets smaller. Okay? So this thing, what it does, maybe it starts up here. Burning velocity is high, so it burns towards this thing. Closer, closer, closer. The closer it comes, the more heat losses it has. The smaller the burning velocity becomes. And at some point, it's just the same. The burning velocity is the same as the flow velocity of the incoming gases. If you would push it a little closer, it would become slower and move down. If you push the flame a little down, it will be fast and move up. Okay, so it's stable. Okay? So that's why this is very nice. You have to consider, though, the heat losses to the burner somehow. So what people usually do is they measure the temperature profile, and in a simulation you would impose the temperature profile. You just say, I use the temperature profile from the experiment and just compute the species, for example. Okay, so this is very often used here to study flame structure, to do measurements maybe for species. One of the problems is this thing is still very thin. It's very thin, and it's hard to measure in a very thin layer. So what people do often with these also, to run them at very, very low pressure. You go to very low pressure, the flame becomes very thick. And we'll see later on why that is. It becomes very thick. And if the flame is very thick, you can easily do measurements. So if you see in the literature, you see a lot of data for these premix flames, premix flat flames, for very low pressure. It's not because people are interested in low pressure, people are interested in high pressure. But at high pressure, the flame becomes so thin, you can't look inside, okay? So especially not with probe measurements. People often do probe measurements, and so, if the probe has to be much, much smaller than the length scale you want to measure, if the flame is thin, the probe can't be small enough. Okay, so these are then the equations that describe this configuration. These are the Navier-Stokes equations, basically, there's no. So let's say you start out with the Navier-Stokes equations, okay? Let's say the momentum equations and continuity equation. And then you simplify this to one dimension. Now you have the continuity equation plus the momentum equations, okay? And then in addition, we need species equations and then the energy equation, okay? And system is closed. Now the first thing you see is if you look at the continuity equation, it basically says the change of rho u is 0. So if you know the density, which you know from solving these equations, you know the velocity everywhere. Okay? You can just integrate this trivial. So you don't need the momentum equation. In 1D, you don't need momentum equations because continuity basically says, the velocity doesn't change, or it changes only if the density changes. So these are just these equations in 1D. Look at this J. J here is the diffusive flux. There are different approximations for how to write this, more complicated and simpler ones. What else? Chemical source term here. This is the chemical source term of species, m dot I, and this is the enthalpy of the species, and so this sum here, that's the chemical source term. Interesting is, you might have seen this before, diffusion of species also causes a heat flux. Is simple. If you have a species here, I have one species here, and they diffuse into each other. Now this species carries energy, and this also carries energy. So if they just diffuse into each other, they also move the energy with the species. If all Lewis numbers are 1, this term goes away. If Lewis numbers are not equal to 1, you have maybe this goes this way much faster than the species goes the other way. So there's a heat flux by species diffusion also. Okay, and pressure term here. So this is the low Mach number limit. This is an approximation, this approximation comes from an asymptotic expansion for low Mach number. And turns out, if you do that, then the pressure, essentially, so all the acoustic pressure waves, they disappear from the problem. There's one pressure is left over in the momentum equation, that disappears here also. And then this is the thermodynamic or the background pressure that you would compute with the equation of state. And you see the pressure only remains here if you have a temporal pressure change, like in an internal combustion engine. So in a flat flame burner, this term here also goes away. Okay, these can be solved. As I said, you can integrate the continuity equation is trivial. Rho u is constant, or rho u is the same as the rho u at the inlet. The velocity at the inlet, of course, is the same as the laminar burning velocity. And so rho u at every point is the same as rho u times SL. So you see that's how SL comes in. And what's interesting is that because you have the system of equations and you have a certain set of boundary conditions, the problem is overdetermined. Okay? So overdetermined means this. So what are the boundary conditions here? Boundary conditions would be, I specify at the inlet, I specify the temperature and the species concentration and everything, or the species mass fractions. And far downstream, I want all the gradients to be 0. Okay? It's all equilibrium. But then in addition to this, if I have if I have an unstretched propagating flame, if I have a flame that's not attached to this burner, then also the gradients in the unburned have to go to 0. So if I have a flame that is just freely propagating through this space, then in the unburned the gradients go to 0, and the burnt the gradients go to 0, and at the same time you need to specify the inlet composition, let's say, and you see there's a second order equation. So this here is a second order term. Second order equation. You can specify only 2 boundary conditions, but you have 3, and because of that, there must be some eigenvalue that makes the third one satisfied, and that's the laminar burning velocity here. So the laminar burning velocity comes in at an eigenvalue. If you have this burner stabilized flame, though, then there's no burning velocity. Then rho u is just whatever you specified at the inlet. Okay, so this is an example here for calculations of burning velocity using these equations. This here is a simple, very simple methane mechanism. And what you see here is that you go very lean, the burning velocity gets very small. It actually doesn't burn beyond or at equivalence ratios lower than a certain limit, which we call the lean flammability limit. And then when you go very rich also, the burning velocity is small. And then you see it peaks here typically at about 1.1 equivalence ratio, slightly rich. These are experiments here. Oh, this here is by Professor Law, actually, you see. Experiments, and then there are 2 different simulations. One just using all the C1 species for methane, no C2 species. And then one uses also C2 species, and you see that's more accurate. And, which kind of tells us that that the C2 species are important for getting the burning velocity right. We'll see later on why that is. What's interesting here is really this, if you think about it. Would you expect that if you consider all the C2 species, the burning velocity is higher, or would you think it's lower? It's higher, obviously, but the question is, what would you expect? Think of what you try to burn. Here's methane, okay? Methane goes to methyl radical, goes to smaller species, CO, CO2. Okay? That's the C1 chain. C2 would be this. Methane goes to methyl, and then 2-methyl go to ethane, C2H6. Goes to C2H5, C2H3, smaller, somehow smaller. So, that's a detour, right? You either go directly to, in the C1 chain to CO and CO2, or you first go to C2 and then you need to go through many other species. Which one is faster? C1 or C2? I would say C1 is not true. Why? Because it doesn't matter how many intermediate species you have. What matters is the character of the reactions that happen. We'll see later on, there are reactions that produce radicals, chain branching reactions, they make things very, very fast. And the other reactions that consume radicals, chain breaking reactions, they make things very slow. If I go from A to B in one step through a chain breaking reaction, a radical consuming reaction, this will be very, very slow. If I go from A to B through A goes to B goes to, no, what did I say? A to B. A goes to C, D, E, F, G, all the way to Z, and then I go to B. And there's no chain breaking reaction, this can be very fast. Okay? So don't think just because it involves a large number of reactions, it's slower or faster, it's slower. Always look at what's the character if you go through the whole chain. And we'll see later on why that is, why the C1 chain is so slow. This is just a preview. Okay, there's another example here. Propane, you see you get different values, whatever, but it looks quite similar in a way. Typically, SL decreases with increasing pressure. It's very simple to imagine why, because let's say a flame burns, I'm not sure if there's a good explanation, but let's say a flame burns a certain mass per time. If pressure is higher, then you have more mass in the volume, and if you burn the same mass per time, the flame is slower. And then at the same time, it increases with increasing preheat temperature, and that makes a lot of sense. If you increase the temperature of the reactants, the flame will burn faster. This is also interesting. We'll see this later on, because think of a combustion engine. Combustion engine, internal combustion engine, what do you call it? A gasoline engine, spark ignition engine, okay? How fast is the flame? So you see here, at stoichiometric conditions, propane here maybe is 40 centimeters per second. Do you think in a spark ignition engine it's faster or it's slower? Faster. And why? Temperature is higher, right? But the pressure is also higher. So there's some compensation. Okay? You go to high, you have isentropic compression. You increase the temperature, gets faster. You increase pressure, gets slower. Okay? You will see later on. It's faster, but it's not so much faster as one might think. It's not much faster. Okay, so now burning velocity is fundamental property of the flame. This is basically it's a given value for a certain chemistry. The burning velocity. Some people, by the way, sometimes people call it flame speed. I call it burning velocity. Same thing. You know, I don't care. Whatever you want to say, whatever is your favorite. You know, your favorite term for this quantity. Flame speed, burning velocity. Right. So burning velocity is fundamental property, is a given value for a certain fuel. Let's say I take methane at atmospheric conditions with air, then this is a given value. You know, you can measure it and it should always be the same. So this can be used to determine flame dynamics. I mean, to compute what a flame does in three-dimensional space in a velocity field, but it can also be used just as a thermochemical parameters to study chemical kinetics, make sure that all the rates are right or so. And but as I said earlier, the flame velocity, it is influenced by other parameters like curvature, and we see this very easily here in this Bunsen flame. And we need to consider things like curvature or the effect of the flow field on the flame. So now what we'll do next is, so we'll look at this, but first we'll look at the flame shape. So we'll look at how to compute flame dynamics. We derive an equation for this, and then we look at these external influences like curvature, Lewis number effects, and then also talk about flame instabilities. Okay, so field equation for the flame position, that is the so-called G equation or the level set equation. You can imagine that now if I have, let's say this room here is filled with a fuel-air mixture, and I spark it here in the corner, then I have a flame that moves through this room, okay? And that flame, let's say, for now, we say this flame is really, really thin. And so I can treat it as a discontinuity, or as a front, and I just need to determine the location of the front as a function of time. And then, you know, I know everything that is to know about this. So there are different ways in applied mathematics or whatever. There are different ways of how you can track a front. And one is this level set method, and the level set method is what what is sometimes used to do this in three-dimensional calculations. The nice thing is about the level set equation, you track a front, but you still solve a full field equation. So in any numerical code, fluid dynamics code, you always solve field equations. You solve an equation for the velocity, which is a three-dimensional field, or the temperature, which is a three-dimensional field, and so on. And so this level set equation also, it solves for three-dimensional field, but you can use that to determine the location of this front. So this is how this works. We start out again with a kinematic relation here. We introduced this earlier. now the kinematic relation, this here we said this in 1D. We can also write this in 3D. So 3D is the same thing. You look at one point of the flame. Let's look at one point here of the flame. And at one point of the flame, in time, it moves maybe from here to here. Okay? It moves from here to here. How did it get from here to here? By two effects. One is the burning of the flame, and the burning of the flame always goes normal to itself. And the second is just the background velocity, which takes the whole flame and moves it from here to here. Okay? So that's written here now. So this is a three-dimensional displacement, which is equal to the velocity field here plus the burning velocity times the normal vector to the flame front. Okay, so this vector always sits normal to the flame front. Okay, then we want to introduce this level set function. The level set function is it's a little different from the temperature and all these other field quantities. This is why it's called a level set function. It's defined like this. You just define a field, a scalar field, and you say, where this scalar field is negative, I'm ahead of the flame. Where it's positive, I'm behind the flame. Okay? It's very simple. So when the scalar is 0, the isosurface where the scalar is 0, that must be the flame. Okay? How you define the scalar, otherwise, it doesn't matter. It has to be regular to some degree, but it doesn't matter. What people do or you could say, I just said where the scalar function is 0, that's where the flame is. You could also say where the scalar function is 5, that's where the flame is. It really doesn't matter. You just define one isosurface of the scalar and say this must be the flame surface. And then I have values larger than this, which would be ahead of the flame, and smaller than this, behind the flame, or vice versa. Doesn't matter. Okay? So, to make it simple, what people mostly use is to define it as a distance function. So the level set function defined as a distance function basically means if I have a flame surface that looks like this, maybe, and let's say this is unburned here, this is burned, so this moves in this direction, then I would just say each point here, at each point, the value of this level set function is the distance from the flame. Okay? So here it would be maybe it's -5, and here is -3. This would be this distance. This would be always normal to the flame front, the closest normal to the flame front. And this here would be 3, and this would be, 7, whatever. Okay, and then you see if I have this whole scalar field, then where the scalar is 0, that's where the flame is. Okay? It's not so hard. It's relatively simple. So this means the flame is defined as, so G, that's our level set function. G is, where G is equal to G naught, there's a specified value. Let's just take this as 0. Where G is equal to 0, that's where the flame is. Okay? So then we can say the substantial derivative. I need to rewrite these two slides. They're not written very well. But then you can say, so on the flame front, G is equal to 0. Okay? So I can say the substantial derivative, dg dt, for G equal to 0, moving with the flame front, that has to be 0. Okay? So if I sit on the flame front and I move with the flame front, then the value, at my feet shouldn't change. It should always stay 0. So that's the equation. I can write this like this. This is dg dt plus basically dg dx dt, where this here now is the velocity of this point that I'm sitting on, of the flame front. Okay? And now the dx dt, that's our kinematic relation. I can just plug this in. If I plug this in, you see you get dg dt plus v dot del g. Okay, this is the first term here. And I get a second term is plus SL times n times del g. Okay? So we put this on the right-hand side because this is the propagation. Now we have the normal vector here. If I have a scalar field, I can write the normal vector like this. If I have a scalar field G, then the normal vector is just del G divided here by the magnitude of this gradient. And if I plug this back in here, then you see this is what you get. Okay? So this is, I mean, it looks like a simple equation. Turns out that the numerical properties of this are a little complicated. So numerically, it's not so trivial to solve. It's not like you solve the temperature equation. First of all, you see it has no diffusion term, so there's nothing that smoothes out the field. Secondly, we derived this equation. Really, I mean, this is a funny thing. We have a field equation. This, you solve this everywhere in the three-dimensional field. But really, we derived the equation just for this flame front. We just started with a point at the flame front, and we derived the equation for that point. So this equation is only correct at the flame front. If you say my level set field in the beginning, it's a distance function, that's okay. That's how you initialize it. And then here you have the front. So then a little later, this thing will tell you this is now the isosurface, whatever. So the flame moved from here to here. But the rest of the field is not a distance function anymore. There's nothing here that says it should stay a distance function.
So it can't exist at a steady state? Or what happens to the flame dxf dt? Or it has to be transient?
No, it doesn't have to be transient. I mean, the steady state is just a special form of transient, right?
But everything will be zero, no? The dxf, the dt?
Well, dg dt is zero. That would be the correct solution for a steady state case, right? It would just stay where it is, yeah. Okay? So basically the way you solve this equation is by advancing it in time. And now you have the new front. It's correct for the flame front. But if you want this to be a distance function, then you have to impose this after each step. Okay? So you solve this, you have the whole field, you advance it in time. The only thing you believe now is the location of the front, and then you just initialize every point back to be a distance function. It's called the reinitialization step. And there are different numerical algorithms for this. Doesn't need to be a distance function, it just needs to be regular. So typically, you don't do this this reinitialization at each time step. You do it every 50 or 100 time steps, whatever. But so you can use this equation. I'm just saying it's a little complicated to solve. Interesting is that so this would describe the evolution of this front. You see, if a front looks like this, then it moves on. What's interesting is these fronts, they form these singularities. They form these cusps because there's no diffusion effect. The only thing that would take this cusp away is, again, you see a very large curvature here. And the curvature, now the velocity, the burning speed at this point should be a little larger. And again, we'll look at this in a minute. But what's interesting is that this burning, it always takes out flame surface. You see this here. In the beginning, this flame has a large flame surface, and then the burning, it's by itself takes out the flame surface. Easy to see also if I start with a flame like this, that you see this here just propagates in this direction, and then this here propagates normal to itself, so a little later it looks like this, and a little later it looks, going the wrong way, it looks like this, and a little later it looks like this. Okay, so the burning itself, so if you have a corrugated flame, the burning itself always takes these corrugations away. It tries to make everything flat and smooth. So that will become important again when we look at turbulent flames. So this is just a preview here of how you could compute these. There's an example here that gives you analytic solutions here for this burning velocity, for this Bunsen burner. By the way, I put this little star here now. Yesterday afternoon, I spent the whole afternoon putting these little stars there, so the next generation of students will have, even if they're black and white handout, they know which parts we skip.
So does this equation only hold for the flame or for all the field?
Pardon?
For all the field
This is only for the flame surface. You could, now you're talking about the flame structure, how that is represented here, or?
I mean, if you need to solve all the field of the G.
Oh, yes. So you basically, let's say you solve all the field, but if you want to save computational time, you can solve it only in the vicinity of the flame. That's what people do. Maybe just solve it in the vicinity of the flame. Just if you have a distance function, you could say, well, I'll solve it only, you know how far away you are in each cell from the flame. You say if I'm farther away than whatever, 10 centimeters or so, then I don't solve the equation. You could do that, yeah. Okay? Okay, so again, there's an example here that you can go through if you want to. And so we want to talk about, so we have seen several occasions now where we said, just this burning velocity itself is not enough. There needs to be some modification due to these curvature effects, and there are different aspects that influence the flame. This is what's called flame stretch. Flame stretch is basically the change of flame area by external influences, and there are two effects that are important here. One is curvature, and the other one is flow divergence or strain. Strain also has an effect on the burning velocity. Now, there are analytic forms that consider, for the burning velocity, that consider these effects, derived here for one-step large activation energy reaction. You get something like this. SL is equal to SL naught. This would be the unstretched burning velocity. And then minus a term that involves the curvature, and then plus a term that involves the strain here. And you see there is this L parameter here, and that is the so-called Mach-Stern length. It's obvious that you have to have some parameter like this, because you see this has dimensions meter per second, this is meter per second, and then curvature is 1 divided by meter, and so there needs to be some parameter that makes this dimensionally correct again. Also, it's obvious there needs to be a length like this, which is now, again, a characteristic number for the fuel or whatever. Because I said earlier, when you have a flame and you have curvature, then if the curvature radius is much, much larger than the flame thickness, then the curvature can't matter. The flame doesn't know anything about the curvature radius or the curvature in general. But if the curvature radius becomes the same order of magnitude than the flame thickness, then you have this interaction. Okay? So there needs to be some length scale that characterizes somehow the flame thickness and the receptibility to curvature. And that is this Mach-Stern length. The Mach-Stern length is on the order of the flame thickness, but also it's not just the flame thickness itself, also it reflects, as I said, the receptibility to curvature effects, which depends also on Lewis number effects and so diffusion effects and so on. So curvature here is given like this, or can be written like this. Again, the curvature is just the divergence of the normal vector, and the normal vector here was expressed in terms of this G field. And then, well, that's what I just said. It's of the order of the flame thickness, but not exactly the flame thickness. But you can call this ratio, the flame thickness over the Mach-Stern length, that is called the Mach-Stern number. Okay? And so there is, as I mentioned, there is also a solution asymptotic analysis that gives an expression here for this Mach-Stern length or the Mach-Stern number, which is down here. And that, is given here, and you see it involves this integral here. It depends on the gamma, here's the density ratio between burned and unburned, and it depends here on the Zeldovich number, so some apparent activation energy, and it depends on the Lewis numbers here and so on. And you see already here that if the Lewis number is 1, Lewis number is the ratio between, I should just write it down here. Or is it written here? Yeah. So it's the ratio between lambda over Cp, that's the heat diffusion, and rho d. Or you could say lambda over rho Cp, that's kind of the heat diffusion coefficient, and d is the species diffusion coefficient. So this is the ratio of heat diffusion by species diffusion. If they're the same, meaning the Lewis number is 1, you see then the second term here, that is 0. And otherwise, this, is a complex interaction here of transport. It's characterized by this term, and chemistry characterized by this term. Interesting here also is that you see that the Lewis number can be smaller than 1. For example, for hydrogen has a Lewis number of about 0.3, very small. Or it can be larger than 1. Typical larger hydrocarbons like heptane or so have Lewis numbers larger than 1, could be 2 or so. And so you could see this can be positive or negative, and depending on what this is, also the Markstein number or the Markstein length can be positive or negative. Okay? That is important. Why is this important? Because look at this. This is the unstretched burning velocity. There's a minus sign here. Typically, the Markstein length is positive, and the curvature here, for negative curvature then, you get a positive contribution here, which makes the flame faster and so on. And it turns out, and then the opposite for the negative curvature, it turns out this is a stabilizing effect. It doesn't make the flame unstable. So if you look at this, flame like this is unburned, this is burnt, propagates in this direction, or we'll see this later on, but propagates in this direction. Then it turns out in these regions here, the burning velocity will be faster, and in this region here, it will be slower. There's a stabilizing effect that takes out these curvature effects. The opposite is the case for negative Markstein number. These here will be slower, these will be faster, so this thing will, after a while, it will look like this and it will become unstable. We'll talk about the instabilities in a minute. Okay, so so I should just say here, maybe at the end, this was derived here by 2 independent sources, Clavin and Williams, and also Matalon and Matkowski. Professor Matalon, I think he taught this course here also before the combustion theory course before. And it depends on the Zeldovich number, Lewis numbers, and so on, which is given here. Yeah. So maybe we'll take a break now, and then we'll meet again in 10 minutes, which is 9:58.